we have the filter experimental spectra that MaxQuant filtered for us. And we have also the theoretical spectra that MaxQuant created for us. And now we're going to compare the theoretical with the experimental. And we are going to do the comparison by using the search engine scoring mechanism that we have in MaxQuant that is called Andromeda. Let's see how this works. So you should think that every time that we are doing Andromeda scoring, we have one experimental spectrum and one theoretical spectrum, and we're comparing these two. When I say comparison, the first thing that we are doing is we're trying to see which peaks match to each other. Of course, with some match tolerance, but yeah, that's the thing that we are doing. And just by doing that, we get these two numbers that are quite important, the K and the N. The K is the number of matching. Actually, the N is the total number of theoretical ion peaks, and K is the number of matches that I have from the experimental spectrum. Okay, so we have these two numbers, the K and the N. And now, actually, this is not the Andromeda scoring. We will go step by step, so don't be confused. So now let's actually calculate something that is the probability of getting exactly K matches by chance. Okay, so I have the K, which I know that is the number of the peaks that actually matched in this comparison of one experimental spectrum with the one theoretical spectrum. So let's see, what's the probability of getting this exactly K matches by chance, okay? And to do that, I will use like this binomial probability, and it's exactly this formula you can see here. So first, you get these combinations. Is the N chooses K, so like the different number of combinations that I can get K matches from N peaks. So this is the first thing in the formula, and then we have the Q divided by 100, which is the probability of getting a random match. And then we have the 1 minus that probability, which is the probability of getting not a random match. So yeah, that was the probability of getting exactly K matches by chance. But I don't want that. I want the probability of getting at least K matches by chance. So what I will do, I will sum up all of these different probabilities from J equals K, which are the number of matches, till N, which is the number of all theoretical peaks. And yeah, this is the binomial probability that we will first calculate, but still this is not the Andromeda score. So after I will calculate this number, I will take the logarithm of that, and then I will multiply with -10. So yeah, I mean, we multiply with -10 because we want, so first of all, this binomial probability, the lower it is, the best, more confident we are about the identification, about the matching. So, but because your score, usually the bigger the score is, the best the identification, that's why we multiply with -10. So yeah, so this is the Andromeda score. And as you understood, probably, we do that for every comparison between the theoretical and the experimental spectra. We call them PSMs, peptide spectral matches. Anyway, so, okay, this is the Andromeda score. So now we talked about a lot of things. So now let's go step by step. When actually you press start in MaxQuant, some of the very important steps that we go through, okay? So now hopefully, like all the pieces that we talked about will make sense now, and we will put them together. So these are not, these are only some of the steps, not all of the steps. But yeah, it is the most important steps, let's say, for you to understand. So we press start, and then the first thing that MaxQuant will do is the feature detection. And what do we mean about that? So actually, let's go here. So MaxQuant will do 3D feature detection, but what I even mean when I say feature? So this probably it's familiar to you in a sense that we saw like this green landscape of MS1 spectra that the mass spectrometer gives you. So this is something similar in a cartoon form. So this is an MS1 level, and you have the M/Z axis, the retention time axis, and the intensity axis. As you can see here, you have all of these peaks. And it was nice when we were talking about how you can get the isotope pattern, how you do de-isotoping, how you get the charge out of your isotopes and all of this stuff. But when MaxQuant opens your files, it just sees these peaks. So it's not very easy for MaxQuant to do all of these steps that we discussed. So it has to start from somewhere. So it will be very nice, for example, if for all of these peaks, we will tell MaxQuant that which ones are coming from the same peptide. So I think we will try to focus on that, to give that information to MaxQuant. And how we will do that, let's see. So first of all, again, this is a part of the landscape that we were talking about. Again, M/Z axis, retention time axis, and the intensity is the height. So when we say 3D feature detection, I'm talking about finding these rectangulars, the color rectangulars outside of the isotope peak, 3D peak. And to do that, we have to go from the 3D plot that we have here to 2D first, and then go again to 3D. So what I mean by that, we have to go one MS scan at a time. So we have to slice the retention time again. So from 3D, we go to 2D. And again to the next one, to the next one, and to the next one. So let's say that from this 3D plot, we get the first slice. So you get some plots that they look something like that. So you have this profile mode that we were talking about. I didn't actually tell you how you go from the profile mode to the centroid mode. So let's see that now. So you have your profile mode, and what MaxQuant will do, it's quite very straightforward. It will look for a local maximum, and then it will go down until it finds 0, or until it finds like a shoulder, something that goes down and then goes up again. So where it finds 0 or a shoulder, it will put like the ends, these red lines. And what it will do later, it will like fit, it will go first to it will logarithmize the data, and then it will fit a parabola it will fit a parabola. So this is like almost similar to fitting a Gaussian into the original space. But yeah, we're fitting this parabola to the logarithmized space, and this will give us the centroid. And the height of the centroid is going to be also the sum of the heights of the peaks inside the red lines. So so we went for 3D to 2D first to do this one, this fitting and centroiding for each one of the slices of the retention time plot. Then what we have to do is that we have to put together the centroids. We have to put together the centroids when they fit together. How we will do it? We go one MS1 scan at a time. So you have your MS1 scan, right? You found your centroid. then you go to the next MS1 scan, and then again you have the centroid there. What you will do, you will see the difference in the M over Z axis of these centroids. If this is less than 7 ppm, then you will group these two centroids together. So, and you do that for the next MS1 scan as well, and the next and the next. Also, sometimes you go to the next scan and there is nothing there. So also, sometimes this happens, so that's okay. Then you go to the next scan. But of course, not if you have 2 consecutive scans without a centroid. But we're okay with 1. So yeah, so then you grouped these centroids together. So as you can see here, now this is in 3D, and this is the same plot, but like looking it from above. And again, the color tells you the intensity. So what happens here, if you see the red outline, is actually what I wanted to do in the beginning. So I told you in the beginning that I want to have the rectangulars, these color rectangulars, right? And actually these are the rectangulars, the red outline here. It's not actually rectangular, it has like this very irregular shape, which is very good in a sense that it will help us to be very precise. And if we have, like, for example, co-eluting peptides, yeah, this very big precision will help us. Another thing that you can check is that in the middle, it's like the different centroids that are grouped together. And you can see that there is also the very wiggly line, right? It's almost like a straight line, but it's really not. Which, yeah, of course, you expect some like irregularities. Yeah, so we did that. Okay, so now we found the features, let's say, but now we have to put together the isotope patterns. So how we will do that? So we will have some criteria to help us do that. So the first criteria, the first of the criteria is that the mass difference between 2 consecutive features, it has to be around 1 over Z, which is, again, we discussed that a couple of times already. It's what we would expect for 2 consecutive peaks in an isotope pattern. So then we have another of the criteria is that the retention time depends on the intensity. So what we mean by that is that so because if all of these features correspond to one peptide, we're talking all of these features correspond to the same peptide, so they should have like the same elution profile on the retention time. So yeah, they should have, let's say, in very like basic terms, the same shape of elution. And then also another thing that we should check is that, so first of all, right now, I just want to put the isotope patterns together, but I don't know the peptides. I didn't do the identification yet, but I know the mass over charge of the peptide for this isotope pattern. So for a peptide with this specific mass, I would expect a specific intensity pattern in the isotope pattern. And this is by using the averaging model. So yeah, peptides are have very similar distribution of elements. So that's why we can actually use that. So when I say we expect a specific intensity pattern, I mean like these heights. So the height of the first peak, the second peak, and the third and the fourth, I expect to be in a specific way for a peptide at this specific M over Z. So these are the criteria, and if they pass all of these criteria, then I group all of these features together in one isotope pattern. So now you can probably tell that for one peptide, I have so many measurements of the mass. So yeah, not only in the retention time, but also I have a lot of 3D features in the isotope pattern. And this will help us a lot. So two things that we can get from this is that we can calculate, so you remember that the line, like also here, the line from the centroid, it was not actually a straight line, but it should be like in the ideal world. But what I can, an easy thing that I can do, I have so many measurements, I can just take the mean of it. So that's great. So what I will do for all of these different measurements, I will take the mean, that it will help me later, we will see. And also I will take the standard deviation of the error of this wiggly line of the centroid. Let's see how this will help us and where. So you remember that I was talking that we go from the very big list of the peptides after we digest them in silico from the FASTA file to a very small list that we actually do the comparisons and the Andromeda scoring. And how how we do that? So for each one of the peptides, we know for your experimental spectra, you know the precursor mass. Actually, also from here, so you will use these two numbers. For the mean, you're going to put the number of the mean in your sorted list of theoretical peptides. And then your tolerance, so how much up and down you will go from this mean, it has to do with the standard deviation. And this is specific for each one of the peptides, which is great. So we're not going to have like general mass error tolerance that we are going to use, but for each one of the peptides, it's going to be a different one. And it depends on how wiggly the line is for each one of the peptides. So now we're in a very good step. So now we went from not knowing anything about the peaks in the 3D plot in MS1 level to actually now at least have some information that I know, for example, all of these peaks that they have the same color, they come from the same peptide. And this is a great way for MaxQuant to start. So that's a great step. So the first step was finished. That was the feature detection. Now let's go to the first search. If you can see here, we have another search as well, which is called main search. Actually, there is another search that it can happen as well. That is not in the workflow now, but if I have time, I will talk about it. But we have at least two searches when you start MaxQuant. Now we're going to talk about the first search that it has nothing to do with what you see at your results at the end in the output tables. We're using this first search just to do recalibration. So let's see what you're going to do. You're going to run Andromeda scoring, and then you will identify some of the peptides. And I think we're using Andromeda score more than 80. So we want very quickly to get some peptides that we are quite confident that they are identified correctly. So that's why we put like a default value of Andromeda score of 80. And we keep only the ones that they're over 80. So for these peptides, I have their identification. So now what I can do, I can have these plots here. So what are these plots? So these plots, first of all, is before recalibration. So you have the plot where the x-axis is the retention time, and on the y-axis you have the error in BPM. So now you can plot like all the dots here that you can see in this plot. They're actually the peptide identifications that you found in the first search. And they're plotted all here, and you can see how we can measure the error. The error comes from the fact that you know, because you have identified the peptides, you know what the mass of the peptide should be, and also you know what you actually measured. So that's why you can actually measure this error in ppm. So when you plot them, you can see that you have this very wiggly line it doesn't mean that it's always going to be like that, but it could be like that. So you have these really systematic errors that a mean will not save the situation here for sure. So you have to do something about it. Also, it's not only this plot here with the x-axis, the retention time, but we do the same with the x-axis, the m over z. Actually, I think you do it also for the intensity for not Orbitrap instruments. But yeah, let's keep it easy. So yeah, so we have these plots again also for the m over z dependent plot. You see also that there is some wiggly lines. It's not like around 0, for example, as well. So of course you have to do something about it. So what we are going to do, we're going to fit a nonlinear model on that. And I don't have a plot about that as far as I can tell. So what you're going to do, you're going to do a piecewise linear regression. And then, yeah, you're going to fit the line simultaneously in both retention time and m over z. And then you're going to subtract the fitting line from the data, not only from this identification from the first search, but from all of the data. And then after you do that, you can see that now the systematic errors, we don't have them anymore. So now you can see that the error is around 0 and it's like almost like Gaussian distributed around 0. That's also another plot that you can see the distribution of the error. So yeah, so we finished with the first search. So we did that we used to do the recalibration, and now we're going to go to the main search. So for the main search, so until now we were talking about Andromeda scoring, and one thing that maybe people are confused about is that they think that this is the scoring that we use to do the FDR calculation, but this is not correct. So we have another step in between. Is we're going from Andromeda scoring to another score that is called posterior error probability. We abbreviate it as PEP, so PEP score. Why we're doing that? So Andromeda is a great way to tell us if a PSM it's actually like a good identification or not, but it's not enough. Or let's say that we have a lot of other features that can help us show us if we should be confident about an identification or not. But the thing is that now you have all of these other features, like for example, yeah, do you have it here? Yeah. You can have like all of these different features, the number of miscleavages, the number of PTMs, the retention time that you can use. But how we can take all of these different numbers and like put them in one number that we can actually use to do FDR or whatever we want to do. How should we sort the PSM in this multidimensional space? And when I say multidimensional, I mean the space that has as a feature the Andromeda score and all the other features that I want to use, the retention time, the number of miscleavages, and so on and so forth. So how we are doing it? We're doing it with this PEP score, which is the probability of a peptide being wrongly identified. So this is a conditional probability. And the really good thing about it is that you can use a lot of different features. So here you can see that is the probability. First, we did the probability of your identification to be wrong, depending on the score. So we only use one feature here. But then you will see that we can use a lot of different features, and that's great. So the PEP score, it's actually very beneficial for us because it's an integration model that we can put different features and gives us a confident measure of how confident we are about our identifications. So to understand why this is important, let's take an example. So here I have a spectrum, and I'm telling you from the Andromeda scoring that Andromeda score like two different possibilities with the same score. So the score is 100 for both of the peptides, but one of the peptides, tryptic, it doesn't have any miscleavages and it doesn't have any PTMs. And the other one has It's also triptych, but also has 2 miscleavages, and it has like 3 different PTMs. Now I'm making a question for you to think about it, which one you think it's more probable to be the correct peptide for this spectrum. So yeah, just think about it a little bit, but in general, we should take the one that we don't have to make a lot of assumptions. So for example, here, for this peptide, we're making so many assumptions. We have to have a peptide that has miscleavages and has PTMs. So probably it's not the correct one. Still, we don't know, but yeah. So yeah, so that's what we're going to do. We're going to go from Andromeda score to PEP score. Again, PEP score is the probability of a peptide being wrongly identified, giving different features. And for the MaxQuant, these features are the score, the peptide length, the number of modifications, the number of miscleavages, and the charge. So how do we calculate this PEP score? So we're using Bayes' theorem. You don't have to be scared. It's going to be quite easy to understand. So again, we have this probability, and we're going to like invert it to calculate it with the Bayes' theorem. So this is going to be equal the probability of having all of these different features based on the fact that the identification is wrong. Then we multiply that with the probability of any identification to be wrong. And then we divide that with the probability of like having all of these features that we were talking about. So it looks quite daunting maybe, but it's quite easy to calculate. So this probability, so the probability of having all of these features when you know that the identification is wrong, you can get this number just by having histograms. You're going to the reverse hits because you know that these are the hits that they are wrong. And then you're going to calculate how many of these having these features, this specific score, this specific length, peptide length, and so on and so forth. So that was easy. So now let's go for the denominator. So this also it's an easy thing. You can take it from all of the hits. So doesn't matter if it's target or decoy. You just count how many of these peptide identifications have these features. Again, this score, this peptide length, and so on and so forth. So again, that's quite easy. The only problem is about this prior probability, the probability of the identifications to be wrong, which is, yeah, it's hard to, it's your prior probability. What do you think about the word? Which, yeah, it's quite hard to put a number there, but you actually don't have to, because it's just like a number that is going to be multiplied by for all of the peptides. So we don't actually even calculate that. So great, so now we calculate the PEP score for the identifications. And now we are going to use this score to do the FDR calculation, not the Andromeda score. So let's see. Now, another thing is that we do that by using this probability, the PEP score. But also another way that we can do it is that you can use machine learning and see this problem as a classification problem. And using all of these features for your classification problem. And of course, you have to use the target and decoy labels for that. But yeah, there's another way for you to do that. And for example, Calculator is doing that. And maybe we also have it also in the next Andromeda 2.0 maybe, to be able for you to choose if you want to use also machine learning or you want to use this posterior probability score. Yeah, actually, we already have for the DIA algorithm, we have in the machine learning way to do this, but not for the DBA, but soon. So yes, so any questions so far? Yes, the question there and here. How much time do I have, guys? 5 minutes? Okay, maybe one question and then maybe we have a Q&A later, so you can ask later.
So I just a bit confused about these different steps, feature detection, where you
Yes.
explained there were 2D peaks,
Yes,
where one of the condition is when the difference between masses is less than 7 ppm, they will be assembled together. But then there's also isotope pattern assembly. Is this a separate step, or these two small steps are all part of this 3D feature detection?
there are different steps.
Are there
So
different steps?
the centroids are putting together with this 7 ppm thing that you were talking about. And then to put the isotope patterns together, you have the other 3 criteria that I was talking about, that they have to be like in 1/z thing. And like the retention time profile should be similar for everybody. Let's go quickly. Where was it? Yeah, so there are different steps. Yeah, here. These are the criteria to put the isotope features together. And the 7 ppm is to put the centroids for one 3D feature together.
Okay. And the second question is when you were showing this recalibration,
Yes.
and then you showed this error, and where are this error coming from? And
yes. So the error comes from, so now you have a mass measurement for the peptides, what you saw in your experiment and what you would expect from just theoretical, because now you have your peptides. So you know what you would expect to measure and you know what you actually measured. And if you subtract one from the other, you get this error. Yes.
And what you do in this recalibration, you sort of change the masses so that they more similar to the expected mass, right?
Yes,
okay,
correct.
Thank you.
Yes,
thank you
you're
very much.
welcome. I think we don't have time. I just have to go quickly. But again, we have a Q&A session later in the day. So yeah, now we apply PSM FDR. So again, I was like spoiling it from the beginning, but I didn't actually say how we do this FDR because I wanted to talk about this PEP score first. So now you have for each one of the identification, this PEP score. Now, what we are going to do, you're going to sort this matrix of the identification based on this PEP score, okay? And then after you sorting, you're going to go one line at a time until you reach the FDR that you want. And the FDR, how we calculate it, is the number of the decoy hits divided by the number of target hits. So yeah, it depends. If you want 1%, FDR is going to cut in a different PEP score, and so on and so forth. So yeah, and then the protein group assembly, yes. So we were talking so far about peptides, but now the peptides are going to be only the means to do the to go to proteins. We don't really care about peptides except if you do peptidomics, for example. So we care about the proteins. So how we're going to go from peptides to proteins, we have to do this protein group assembly that we call them in MaxQuant. So let's say here we have an example. Let's say that there are the 4 peptides that we identified in MaxQuant. And then there are these 2 proteins, protein A and protein B. Protein A have all of these 4 peptides. Protein B has only one of these 4 peptides. So the thing is that protein A is sufficient enough to explain all of these identified peptides, but that doesn't mean that the protein B is not in our dataset. So we cannot. So what we are going to do in MaxQuant, we're going to put these proteins together in a group. So what happens is actually in the beginning, each protein is going to be its own protein group. And then you do all the combinations between the different protein groups or proteins in the first step. And then you see if a protein has the same number, the same peptides as another protein group, then you put them together. Not only if they have exactly the same peptides, but also if they have a subset of the peptides. So that's the 2 rules. if they have the same or a subset of the peptides, you put them together. Then another thing that you have to think about it now is that there are some, so you put the protein groups together, but there are some peptides maybe, and usually it happens, that they correspond to more than one protein groups. So what happens with these peptides? These peptides are going to be used for quantification. I know that I'm going very quickly, but I'm really sorry about that. But these peptides, again, the peptides that correspond to more than one protein groups are going to be used for quantification only once. And they're going to be used for the protein group that has the more number of identifications. That's it. Last thing, so we did PSM FDR, and that's not enough. We have to also do it in protein FDR level because PSM doesn't say anything about the protein FDR. It usually inflates a lot because what happens is that, like, first of all, the peptides, the proteins don't have like the same length. And also usually what happens is we identify the same peptides again and again with different PSMs. Anyway, we have to do protein FDR also. We have to do FDR also on the protein level. And how we do it in MaxQuant, we are going to calculate this protein score. So it's going to be the product of the peptide PEPs. And then after we calculate this product, we're going to take the logarithm of that and then again multiply with -10. And this is going to be the protein score. Then we're going to do exactly what we did here. We're going to sort the protein list now with the protein score, and then we are going to find the value that gives us 1% or whatever percent you want FDR. And that's, I think I should stop here because, yeah, we have another presentation from Tammy. So yeah, thank you so much. We will have Q&A later. So I know that I went very quickly. So maybe you can ask some questions later. Yeah, so thank you.